Hi everyone, it's Michael. So I have another very fun problem for you all today. This one was posted by the Art of Problem Solving forum by Parmenides, and it's from a competition in Ukraine in 2002. So a simple configuration, so if you'd like to try to solve it, feel free to pause the video. Alright, so I'm going to go over it. So we have a point P outside of the circle omega, and it's tangent to the circle at A. And then there's another line through P that intersects the circle at points B and C. We draw the two tangents to the circle at B and C, and they meet at point Q. And then AQ meets BC at K, and we want to show that OK is perpendicular to PQ. So the main reason why I wanted to put this problem on my channel was to illustrate the concepts of poles and polars. I think this is an absolutely fantastic problem for illustrating the idea. And like I mentioned in one of my earlier videos, it's a concept that I feel like I haven't shown as much on my channel relative to how important it is. So this problem, for those that know it, it's not a very hard problem. But for those who don't know the concepts of poles and polars, I feel like it'll be very instructive. Okay, so so ultimately we want to show that OK is perpendicular to PQ. But since QB and QC are both tangent to omega, that means that the line BC is the polar of Q with respect to omega. So like I mentioned before, the polar of Q, it's the line so that OQ is perpendicular to it, and also the distance from that line to O times the distance from Q to O is the radius squared. So it's a property of polars that if you have a point and you take the two tangents to a circle, then the line connecting the 2 points of tangency is the polar of that point. So I'm going to write this out. So QB and QC are both tangent to omega. So line BC is the polar of Q with respect to omega, and P lies on that line. Okay. So then by Lahir's theorem, if P lies on the polar of Q, then Q also has to lie on the polar of P. So if I draw the two tangents from P to the circle, Q would have to pass through the line connecting them. And so I'm going to label this point D. But like I said, since P lies on the polar of Q, Q has to lie on the polar of P. So this intersection point D, PD has to actually be tangent to the circle, because the polar of P is the line joining the 2 points of tangency. So AD would be the polar line, and Q lies on it. Okay. So where do we go from here? We want to show that PQ is perpendicular to OK, and I'm actually going to show that PQ is the polar of point K. And I'm going to use Lahir's theorem again. So K actually lies on the polars of both point P and Q. So that means both P and Q have to lie on the polar of K. So I'm going to write this out. But so like I mentioned, PD has to be tangent to omega. And K, it lies on the polar of P because it lies on AD. And so P has to lie on the polar of K by Lahir's theorem. Okay. And then similarly, K lies on the polar of Q, so Q has to lie on the polar of K. Okay, so both P and Q both lie on the polar of K with respect to the circle. And so that means the line PQ has to be the polar of K, because if both of them lie on the polar, well, there's only one line through 2 points. So line PQ is the polar of K with respect to omega. And therefore, by definition of polar, it has to be perpendicular to OK, which solves the problem. It also has the property that if you take the distance from the line PQ to point O and you multiply it by the distance from K to O, it's equal to the radius squared. But we don't even need that fact. We just need the fact that the line PQ is perpendicular to OK. And that solves the problem. So I might do a video on Lahir's theorem soon, or on other properties of poles and polars, because I feel like it's about time I do a video on it. But I feel like this problem was a really nice illustration of the concept. So if you liked the video, give it a thumbs up. And if you want to see more like this, feel free to subscribe to my channel. Thanks, everyone.